The first model of the atom that we referred to was the Dalton solid sphere model of the atom. Remember we talked about Horton Hears a Who, and we said that speck of dust, there's nothing smaller than a speck of dust, or at least that's what everybody in Horton Hears a Who, other than Horton, thought, was that there was nothing smaller than a speck of dust. There could be different specks of dust, but they're all fundamental things. Okay, well, Dalton's solid sphere model of the atom said that atoms are fundamental. There's nothing smaller than an atom. Atoms are different from one another, but you can't get anything smaller than an atom. You can't separate it. But then we talked about the cathode ray tube experiment that was performed by Thomson, where he discovered the electron by finding the charge to mass ratio. And we realized that there was something smaller than the atom. There was electrons. And Thomson said that these electrons didn't orbit, but rather they just floated around in a sea of positive charge. We call it the chocolate chip cookie dough model of the atom, or the plum pudding model of the atom, or the, you guys usually hear it, I guess, is the raisin bun model of the atom. That was revolutionary because it acknowledged the existence of something smaller than the atom itself. I would argue that this one that we're about to talk about is revolutionary as well. It doesn't acknowledge the existence of subatomic particles because that's already done, but it does give us much closer to what we currently accept is the structure of the atom. It's still not perfect. In fact, there's still a long way to go, but it's a huge step forward over the Thomson plum pudding or raisin bun model of the atom. Let me describe an experiment that Rutherford performed in determining his model of the atom. This experiment involved having a box of radioactive material that would generate alpha particles. These alpha particles would leave this box one at a time. As the nucleus decayed, the alpha particles would leave that box. Those alpha particles were directed towards a, I don't want to call it a screen exactly, but a thin gold foil, literally made it of gold. It's like aluminum foil, except it's made out of gold and a lot thinner. You guys know what I mean by when I say gold leaf? That's used in baking sometimes for decoration and baking. You actually eat it. And it's actually gold. It's really, really thin and really, really light, and that's why you can afford to put it in baking. That's what we're talking about, something thin like that. Incredibly thin gold foil. Now this thing is going to be surrounded by what we call a scintillation screen. I don't care if you remember that scintillation word or not, just call it a screen. When alpha particles strike the screen glows. So we know where the alpha particles hit. As Rutherford and his assistants, one of his assistants, by the way, name was Geiger. You ever heard that name before? Geiger, where have you heard that? Geiger counter, yeah, same guy. One of his assistants, one of his graduate students, Geiger, and his other one was Marsden. His name was Marsden. These three guys, Rutherford and his graduate students, fired these alpha particles one by one at this gold foil, and they observed where they went. They observed where they struck the screen. They found that most of these alpha particles ended up going straight through. They just went straight through the gold foil as if the gold foil wasn't even there. It's kind of like you got 110 people lined up on a Canadian football field at 1 yard, at 2 yards, at 3 yards, etc., all the way down to the other goalpost. We blindfold them. We direct them in the right direction to send them straight across. The vast majority of those people will end up running straight across the football field. If we line them in the right direction and they can't see, they're not influenced by anything, they're going to go more or less straight across. At least most of them are going to go more or less straight across. Let's say of the 110 people we have running across the football field, let's say 100 of them end up going straight across. I'm making those numbers up, but most of them go straight across. All right. Not all of them go straight across. So remember, we had 110 yards on a football field. Only 100 of them went straight across. What happens to the other ones? Well, some of them are deflected. some of them veer off of the straight line path. Just like, let's say, 8 of the people running across the football field end up on the other side, but don't go in a straight line to the other side. So if they start on the 37-yard line, they end up at the 26-yard line. They end up changing their path. Their path ends up being deflected as they go across. A few of the alpha particles, just like a few of the people running across the football field, end up bouncing back. So they hit the gold foil, and then they bounce back like this. Not very many of them. We got 110 yards on a Canadian football field, only 2 of them. Only 2 of the people running across there bounce back. Now let's try to come up with an explanation for the people running across the football field and the observations that we've made with those people. The fact that most of those people went straight through would tell us what about the football field? Yeah, it's got a ton of space. Most of the football field is empty space. There's nothing to run into there, and most of the football field, so most of the people went straight across. That would be the same deal here. Most of the atom is empty space. Not all of it, but most of it's empty space, and that's why most of the alpha particles were able to go straight through. Some of the alpha particles, some of the people running across the football field are deflected. What would cause them to be deflected? Maybe there's something in the middle of the football field that would cause the people to be deflected. Maybe something that repels the people running across the football field. What would repel an alpha particle? What would repel a positively charged alpha particle? Sorry? No. Something positive would repel a positively charged alpha particle. So we have to have something small and positive in the middle. It has to be small because most of it's empty space. It has to be positive because it has to be something that repels the positive alpha particles. Small, positive, we'll call it a nucleus. There's the discovery of the nucleus right there. We got a small positive nucleus in the middle. Now, 2 of the people running across the football field bounce back. What does that tell us about that small positive nucleus? Down it? It's got to be pretty solid, right? Pretty heavy or pretty dense. Okay, maybe there's this big football player, weighs 250 pounds in the middle of the football field. Okay, McKenna runs across, bounces right off that football player. If it was a 4-year-old in the middle of the football field, what would happen? McKenna would just run right through that kid, plow right through that kid, and knock him out of the way and end up on the other side, right? Yeah, I like to think so too, but that small positive thing in the middle must be dense or heavy in order to cause the alpha particle to bounce back. This leads to a model of the atom that looks a lot different than the plum pudding or the chocolate chip cookie dough or the raisin bun model of the atom. This leads to the model of the atom that says we have a small, dense, positively charged nucleus, mostly empty space, and then the electrons orbiting around that nucleus. We sometimes call this the planetary model of the atom. And it's what I consider to be revolutionary because, man, this sure looks a lot like the model of the atom that we currently have, right? There are differences. There are important differences from this, between this and our current model of the atom, but it sure looks an awful lot like it, the basic structure. Niels Bohr comes along, thinks he can refine that model of the atom, the planetary model of the atom. Niels Bohr looks at what Rutherford found and says, yeah, you know what, I agree with the fact that there's a small, dense, positive nucleus there. I can live with that. The fact that most of the atom is empty space, sure, I can live with that too. Electrons orbit around the nucleus, yeah. So what makes the Bohr model of the atom different from the planetary model of the atom? If all of those observations and that Rutherford made, Bohr accepts. Yep. The electrons, you mean? Yeah. Good. Well, yeah, you know what, actually? Almost the opposite, actually. But you're on the right track, for sure. Um, the electrons can't just go anywhere they want. Rutherford said the electrons have to orbit around the nucleus in a circle, wherever they want. Bohr said that the electrons have to orbit around the nucleus on specific levels. So he acknowledged the existence of electron levels. If you've taken chemistry, you know that electrons can exist on the first level, the second level, whatever. There's 2 electrons, max 2 on the first level. I think it's max 8 on the second level, and so on and so on. You don't need to remember those numbers. I don't remember those numbers past the second or third one. Don't worry about that. You just have to know that they're on they're on their own level, and each level is characterized by a specific energy. So the energy of the electron on the first level is different than the energy of the electron on the third level. The second observation, we call it stationary states. Electrons, as they orbit around the nucleus, watch my keys as I swing around my head here. Electrons, as they orbit around the nucleus, go in a circle. Whether they're on levels or not, they go in a circle. As they go in a circle, they experience a centripetal acceleration. According to Maxwell, a centripetal acceleration or any acceleration of a charged particle should generate EMR. But it didn't. We know that it didn't because if these electrons experience a centripetal acceleration and emitted EMR, if they accelerate toward the center and emit EMR, then they would lose energy. And as they lost energy, they would spiral into the nucleus, just like my keys just did. That doesn't happen. So it's as if they're not accelerating. It's as if they're not even moving. It's as if they're stationary. It's as if they're in a stationary state. Finally, the third aspect of the Bohr model of the atom that differentiated it from Rutherford's planetary model of the atom talks about electron transitions. Electrons can jump to a higher level. You go to the Saddledome for a hockey game, and your seats are up there at the row 20 of the sport check zone. You got to go up to a higher level. What do you better make sure you've done? Make sure you've had supper. Make sure you've had pasta the night before. Make sure you've just had a coffee with some caffeine to give you some energy. You need to absorb some energy to get to that higher level. Usually that energy in the atom would be EMR, but not necessarily. Any form of energy, including from another electron striking it, could cause the electrons to jump to a higher level. But if I'm in the third deck and I see 2 seats open down there in the first deck, what am I going to do? I'm going to move down. If there's a vacancy, electrons will fall to a lower level. What do you think they do when they fall to a lower level? They lose energy or they emit energy. And that energy will be, not usually, but it always will be in the form of EMR. First day of our last unit, we talked about how different types of EMR were produced. Remember, infrared, visible light, ultraviolet were all produced by transitions of electrons in the atom from higher to lower levels. Here we go. Okay, we'll spend some time tomorrow talking about more details of the Bohr model of the atom, but that's good enough for today.